Well, hey everyone, and welcome back. You know, when we talk about pressure with respect to geology, one of the first things that comes to many people's mind, mine included, is faulting. Now, you'll recall that faulting occurs when we've got just a force acting on some strata. We'll call these A, B, C. And this force can be in any direction, meaning it can be compressional, pushing them together, tensional, pulling them apart, or shear, which is where they scrape side by side, like at transform boundaries. So let's just give a quick example here. This would be an example of something compressional, where we've got these two being pushed together. It's a force that's being constantly applied, and over time, sort of like in physics, where you need a force that overcomes the coefficient of friction in order to get something to move. Like if you're on a surface of high friction, maybe you can put something on a slope and it won't slide down immediately. That's what this is like. You've got this force that just builds over time until it overcomes a certain threshold, at which point it breaks and we get some brittle failure, and the rocks just shift suddenly and we get a change in position. Pressure is released, and many times we get earthquakes. But the fault would look something like this. Let's just say it's a normal fault. Our footwall is upthrown. So now that's A, that's still B, and that's C. But now maybe if it's a normal fault, then the footwall's been upthrown. So maybe B has been shifted over here on this side. Now A's all the way up here. C is here, and maybe a small layer down there called D has been revealed. Now that's faulting, which we think about a lot. However, faulting can only occur at high pressures and low temperatures. Now low temperatures is important because at higher temperatures, rock becomes more malleable, you know? It's like if you take a piece of clay and start pushing on it, is it just gonna snap all of a sudden? Like, for example, this plastic rule, if I were to push on it with enough force, you know, it has a bit of wiggle room. For a while it kind of bounces back and forth between these shapes. But if I were to just do this and just push on it from both sides, and I applied too much pressure, you know, this is relatively weak plastic, then it would snap. However, if you have something like clay, modeling clay, then you'll see that if you push it together, provided it's not hardened yet, then it'll sort of bend very easily, and it'll just take the shape that, or it'll take a new shape. Maybe it'll bend upwards or downwards, depending on how much pressure you apply in response to that. So rocks behave in a similar way to this image of modeling clay when they're heated, because they become more malleable. That's a property of solids I'm sure you're aware of, where if something's warmer, then it's much less, its molecules are much less condensed, and it can take different shapes more freely. So with rocks, we're not going to see that sort of just dramatic shift all of a sudden and the brittle failure. We're going to see much more gradual deformation that is much less drastic and doesn't result in a violent burst of energy that results in earthquakes. So that's when we get what's called folding. And folding can only occur with compression, unlike faults, which, as I mentioned, are compressional, tensional, or shear forces. But if we've got three layers, and let's say this is deep within the Earth, and it's at a very high temperature, deep within the Earth's crust, I should say, and it's at a much higher temperature than we would observe at the surface, then we could say that these are being subjected to high temperatures and high pressures. Those are the conditions. And now, since we're at high temperatures and pressures, the rocks are going to behave differently. Each strata isn't going to just shift all of a sudden after a large buildup of energy, but the energy is going to cause changes gradually, right? Going back to the modeling clay idea, we're going to just see it sort of bend under the pressure, being pushed together, and they're going to bend either upwards or downwards. So they'll look something like this. I tried to keep the the upper boundaries relatively the same. So let's just say that's A, that's B, and then C is down here, it's been bent too. And then a new layer becomes visible to fill in this gap here. We'll call that layer X. And we get this fold here. And as the name implies, it looks like it's been folded downwards. That's really the basic definition of what a fold is. Now we can get into multiple types of folds. Now, for this video, I'm going to stick to just the bare basics. And as I mentioned, it can either fold upwards or downwards. This one is folding upwards because it opens upwards. The crest is pointing downwards. And when we have that, it's called what's known as a syncline. Syn as in synergy, and cline as in, decline. Just incline or decline, syncline. And yeah, just remember that. For this one, crest is down, and the limbs fold upwards. Now, of course, this isn't the only thing that can happen when you have compressional stress like this. If you think about it, we could also have them pushed upwards rather than downwards. So we can just rearrange the image slightly to show what that looks like. So maybe we've got something like this. Maybe A, B, throw another one down there, C, D's down there. So when we've got something like this, it's called an anticline, which is, formed in the same way. For whatever reason, the pressure may just cause it to point upwards rather than downwards. So yeah, it's just the opposite. The crest is up, the crest points upwards, and the limbs fold downwards. Now there's no real super sophisticated method of memorizing which one's syncline and which one is anticline. Fortunately, there's only two to remember, so it's relatively simple. One of the things I like to think about is, well, anticline, it begins with an A, and if you, these pieces kind of look like they're folding upwards, kind of like the top of an A. You could sort of maybe draw something like that to help you out. Looks kind of like an uppercase A. I don't know, that's just one rather unsophisticated method that I can use to just jog my memory and say, okay, yeah, that's an anticline, not a syncline. Because, you can understand it conceptually, but messing up on just the word that you're trying to assign to it can be embarrassing. And now the final piece I wanted to talk about is just pieces common to all folds. So we'll just draw a generic, we'll have this be an anticline, I guess. And let's just say it looks something like that. And I mentioned these terms earlier. At the top here we have the crest, kind of like the crest of a wave, I guess, if you want to look at this as something like maybe a sinusoidal wave, and just think about it like, oh yeah, crest at the top of this structure. And then these pieces here, you heard me use this term, these are the limbs located to the right and the left of the crest. And these are the actual pieces that dip in whatever direction, upwards or downwards from the crest, depending on whether it's a syncline or an anticline. And then finally we've got the axial plane right here. It's just this line that goes through the crest and sort of makes a very clear divide between one limb and the other. Brief note, you will notice it is called the axial plane, and that's because, well, folds are three-dimensional, and this thing, though I drew it in 2D and I've been using two-dimensional cross-sectional diagrams, it will stretch outwards, looking something like that. So the plane extends with the fold, just backwards. And yeah, those are some of the most basic pieces, but they are common to all folds. We'll get into cases in which they may be harder to define, or in cases where the limbs lose symmetry. But for now, this has just been the basics of folding. Hopefully that was informative, otherwise good review. Hope you guys enjoyed, and I'll see you all in the next video. Ciao.